Bon, on va reprendre là. It's like children. So our next speaker is Eva Deelman from USC, and she has a lot of experience in workflows, and she has been working on Pegasus. And we are quite lucky to have her today and to share her expertise with us. Thank you.
Merci. Bonjour et merci beaucoup de m'avoir invité ici à ce forum. C'est un vrai plaisir d'être à Paris. Quand j'étais une petite fille, j'habitais dans la maison à gauche dans ce plan, dans le 17e arrondissement. But the rest will be done in English. Thank you very much. It's a pleasure to be here. I wanted to talk a bit about our work on Pegasus, how it has started. Also, one of the main examples or main applications that we've been working with over the years has been the LIGO gravitational wave observatory application. And basically, they're searching for gravitational waves that are being emitted by objects, heavy objects that move around each other, and they can affect the curvature of space, so that the theory is that they create these ripples through time and space, and potentially you could detect these ripples if you designed instruments sensitive enough to do so. So LIGO has been around for a number of years since the construction has started in 2002, and it started running in the US. It has two large instruments in the US, and you see one of them on the right. And basically this is a central station, let's see, a central station with two 4-kilometer arms, and you have masses suspended in these arms in vacuum. And the theory is that if a gravitational wave comes through these arms, then you'll be able to see the deflection of the masses and detect it with the lasers that measure the deflections. In the first phase that ended in 2010, LIGO did not detect any gravitational wave. They used this time to reset up the cyber infrastructure, set up the instruments, and make sure that if such a wave would go through an instrument, they'll be able to detect it. So actually in 2010, they passed what they call a blind injection test, where there was a fixed gravitational signal inserted into the data, and they were able to detect it with analysis. So they're confident that when they upgraded the lasers and the whole system back in 2015, they will be able to detect a wave should it come through. These instruments are quite incredible. These are just some of the details from the LIGO website. But basically, they're super sensitive. They can measure the distance to the nearest star to an accuracy smaller than the width of a human hair. They also have these tubes that 4 kilometers tubes are the second largest vacuum chambers. So you can fit in 11 Boeing 747s inside of them. And it takes about 40 days to pump down these chambers to the vacuum that you need to do the experiments. And then also because these arms are so long, you have to take into account the curvature of the Earth. So when you design them, you have to make sure that they're perfectly straight and not affected by that. LIGO did detect the first gravitational wave and announced it in February of 2016. And basically, they detected the wave at the two instruments. And even though the first detection, what they saw at the instruments, happened back in September of 2015, it took them several months of large amounts of computing and analysis to do the detection. So if you look a little bit in detail what it took, Basically, it had the three components. They had a science workflow where they described the computations, and so they could measure the statistical significance of a signal that they needed for discovery. They have a variety of sub-infrastructure tools, including Pegasus, to automate the computations. And then they had the sub-infrastructure platform. In this case, they ran on their own computing infrastructure that belongs to the various LIGO collaborators, but also on the Open Science Grid, which is a distributed environment in the US, Exceed, which has high-performance computing clusters, and Blue Waters, that is a cluster as well. For the first detection, they ran about 21,000 workflows, and the workflows contained about 107 million tasks. During this period from September to February, a lot of computations took place, but also a lot of validation of the analysis, making sure that that was a true detection. Once they had the analysis validated, they were then able to use this analysis in a more efficient fashion on the variety of computational resources that were available to them. And so the next big detection that they had in October of 2017, which was a detection of colliding neutron stars. So this was an observable event in other spectra as well. So other telescopes were able to look at the event. It took them only a matter of weeks to do the few days, but not, days, not weeks, to do the analysis. And this is because they had the automation at their disposal, and they had the cyber infrastructure at the disposal as well. If we look at the time that we worked together with LIGO, we actually started working with them back in 2001. And we built the first prototype for them, and I'll talk a little bit more about that experience. Then in 2010, 2011, they passed the blind injection test. And so this was a big event for us. We did a lot of advertisement. But you can see that this generating actually scientific results from a collaboration takes a really long time. So it took 10 years to get to that point that we could say that we had something that was really had scientific impact. And then it took another 5 years for the first detection of a black hole collision and the first gravitational wave. And then finally, 2017, to have this multi-messenger observation. And also LIGO collaborators have received the Nobel Prize for their work. And so what you can see is that you kind of have to be there for the long haul to have impact. You have to develop software that's robust and that can be used by scientists in the long run to be able to have this type of impact. So I wanted to talk a little bit about how Pegasus started. So we first were part of a Griffin project, which was an SF, National Science Foundation funded project. And in this project was a concept of virtual data, and which was basically trying to take the concept of materialization, view materialization databases to distributed environments. And so the user could ask for these virtual data products, and the system would deliver the data if it was already available on some system, or it would generate the data on demand. Then we tried to take these computer science concepts and ideas and translate them into scientific needs. And so we created this virtual data scenario for LIGO, and in which case LIGO scientists could ask to conduct a pulsar search on the data collected from during a particular time frame. Then the system would try to understand the request, determine how it could be satisfied, where it could do the computations. It would then plan out the movement of data as needed and schedule the computation, and then basically give the results to the user. So back in 2001, 2002, we developed the system which was a web system. Basically, the LIGO scientists would fill out a form. And then we explored various AI planning techniques to take this information and develop a plan that would look something like this, that would basically retrieve the data from the archive. It would clean it. It would then take the short time frames that come off the instruments and then put them into longer duration time frames. It would create a time frequency image where you could look for this gravitational wave signal. And if you found something, you'd store it into an event database. And then the user could look at it and look at the significance. What was kind of lost in what we've done, so we showed these interfaces to the scientists, and they basically were not interested in that type of interface for the work. What they really wanted to is to manipulate these workflows to be able to do the analysis. So they wanted something that they could change the parameters on the computation and easily inspect the intermediate results and so forth. So we did lose this scenario of using AI planning techniques to deliver the virtual data concepts, but we found the new research direction of workflow management in distributed environments. And the reason why in those days LIGO is working in a distributed environment is basically the collaboration itself of the scientists was distributed amongst various universities in the US and also in Europe. So what challenges did we see in workflow management? So first of all, we work also with other applications in astronomy and in earthquake science, and they all had similar challenges. So they had the need to describe these complex workflows in a simple way. They needed to access data that was distributed. So in astronomy, the archives are often distributed. The resources that the scientists have are distributed as well. And you need to be able to deal with changes to these resources over time. So things get upgraded, new resources come online. So our focus then became really separating the workflow description, what the scientist has to deal with, from the workflow execution. And then we looked, because of that separation, this implied that we would have to look at workflow planning techniques and scheduling that would allow you to take this high-level description to something that's executable. And we looked at challenges of scalability and performance. We also looked at issues of task execution. So how do you execute tasks reliably? How do you monitor the execution? How you debug in case of failures? So in my talk, I'll give some examples of Pegasus workflows in addition to LIGO. I'll talk about the workflow management system itself, various components and capabilities that it has. And then I'll talk about the challenges that we had over time running workflows in distributed environments and on high-performance computing clusters and clouds. And then I'll talk a little bit about the future directions of what some current research that we're doing in future directions. And then, if I have time, I'll also like to mention a new effort that we have, a large collaboration to build a cyber infrastructure center of excellence. So we have a pilot effort in that direction. So if we look at how workflows start, oftentimes they start on paper or on a whiteboard. This was, on the left, you have an example of a solar fuels application. In the middle, this was actually, I think, from CC Grid I believe, in Lyon. So we had the INRIA paper to work on, and these were collaborators from Germany, from Max Planck Institute, doing helioseismology, and then RNA-seq on the right at USC. Sometimes the workflows are quite large, and they're whole workflow ensembles. So, for example, we worked with scientists at Caltech to generate these galactic atlas of a galactic plane in different spectra. Just for one band, you have about 18 million input images that you need to operate on, which is about 2.5 terabytes of data. They generate 900 of these output mosaics that are put together. They're about 2.5 gigabytes each. And then you do that 17 times for the different bands of the application. And you can use these atlases for performing a number of different to answer a number of different science questions. And for this particular application, we performed the computations on Amazon Web Services. Sometimes scientists don't actually want to see the workflow, so we can hide the workflows behind portals. So this is a project from the National Institutes of Health which has a repository for mental disorders. And so when the scientists submit the data, after they conduct a human study, they submit the data to the website. We do quality checking on the data using workflow technologies, but the scientists don't see that. So in terms of a Pegasus workflow management system, I just want to set a little bit of a context of what we're looking at. So oftentimes when you have a scientist, maybe they have a certain data acquisition system in the lab. They have some storage. They have a local resource, a laptop or a server, and they have a work definition. On the other hand, across the network, they have a number of different resources, and this is an example of a US type of deployment. So we have a campus cluster, you have high-performance clusters of Exceed or a Department of Energy, which is NERSC, LACF, and so forth. You also have these high-performance and high-throughput distributed systems such as the Open Science Grid, and clouds, various clouds which are academic and commercial. However, oftentimes the workload that you have is not exactly right. So oftentimes the scientific workflows, yes, they do have some MPI codes with them, but even in cases where you have MPI, you also have a lot of post-processing that happens on the data generated by these codes. And those post-processing is done usually through single-core computations. At the same time, there are a large number of these computations that need to be done, so oftentimes you want to place them on a high-performance computing environment for execution. Additionally, you might want to be able to change the resources over time or combine them into a workflow, so you can combine your local resources with high-performance clusters and maybe spill over to the cloud. And what you don't want to do is to have to change your workflow definition every time you change resources or combine them differently. So we have this notion of submitting locally. So we place the workflow management system on a resource that's local to the user, and then we compute globally. So we send work and data to the resources that are available across the network. And the scientist has basically the same workflow definition. We just map this onto the different resources based on the needs. If we look at, in that scenario, then if you look at the workflow management system functions, first of all, we need to discover whatever resources that are available to the users, and these are compute resources, data, as well as software that's installed on them, or software that can be deployed on demand. Then you have to select the appropriate resources based on the availability, whether they have the right software, maybe performance, reliability, and so forth. So you need to do this initial selection. And then you need to devise a plan how you're going to map this workflow description that you have onto those resources. And you need to figure out how to move the data, what protocols you need to use to move the data to these various resources, or collocate computing where the data resides. You need to decide also what data you save along the way. And once you have a plan, you then need to execute it in a way that's reliable, and you need to keep track of the data that you generate. And in terms of Pegasus, Pegasus operates on files. Currently, outside of the function of a workflow management system is resource provisioning, but that is changing as well. In terms of Pegasus, it has basically two main components. It has a workflow compiler or planner, which takes an abstract workflow description, which is resource independent. It has some auxiliary information, so we have cal logs that tell us about what resources are available, what services they're exposed, for example, for job scheduling or data management, where are the codes installed or which codes can be installed on demand. And then the output of this planning process is an executable workflow now has a description of the concrete resources that are being used for computations. Also, Pegasus automatically locates the data for both the workflow tasks, for the workflow tasks, and also it moves the data to where it needs to go. And finally, we also do some transformations for performance and reliability, which I'll talk a little bit about next. Then once we have a plan, the plan is given to a workflow engine. In particular, we use the Contour Deelman. It follows the plan that Pegasus has devised, and then it sends the tasks to through the Contour Schedule, it sends tasks to the remote resources. We also wrap all the tasks with Pegasus Kickstart, so it's a thin wrapper that allows us to collect performance information while the tasks are running. We also store provenance information, so everything that's done by Pegasus and happens to the tasks is being recorded and stored in a database. And we also keep track of performance information in a database as well, and also more recently in Elasticsearch, so we can mine that information. In terms of the various ways that people can generate workflows, we provide a variety of tools, APIs. So at the beginning we had Java and Perl interfaces. Later on Python came about, and we included that as well. And recently also we integrated Pegasus with a Jupyter Notebook. And a lot of bioinformaticians also are using R, so we have an R API to create these abstract workflows, which internally are in XML. And then once you create that workflow, you can give it to Pegasus. You have information catalogs that are either populated by the user or by collaboration. So in some cases, like for the Open Science Grid, they provide this information to us through the catalogs. Also in terms of data allocations, this is something that collaborations such as LIGO provide. So you basically start off with this abstract workflow, you take the information about the environment, and you create the executable workflow that you see on the right. You have nodes, you add nodes to the workflow to stage the data, for example. You then concretize the tasks in the workflow, so you actually put in commands that need to be executed on the various resources. You stage the data out to where the user wanted it to go, and you also register the data for the workflow. You may also add registration tasks throughout the execution if you want to save the intermediate data products. As a result, also we have various monitoring tools that allow you to look at the execution of the workflows. It shows you the various information about the success and failure of the tasks. It, it also provides performance information. So this is the basic functionality of Pegasus. And now I'd like to talk about the various challenges that we faced in the execution of workflows in a variety of environments. So oftentimes we see a number of failures, especially in distributed environments. That can be failures due to resources failing or application failing, or also cases if you're running, for example, on a Contour pool and you get evicted from a particular node, you also consider that a failure. Another problem is that there are storage limitations on execution sites, and if you're running really large workflows, you might have trouble fitting a workflow with a particular execution site, so that's another challenge. Also, as I mentioned, a lot of workflows have a number of single core, often very short running tasks, so that's also an issue of performance and even feasibility of running them on HPC systems. And then we have a heterogeneous execution architecture. So you have different systems such as Craze, Blue Jeans, and others. You have shared versus non-shared file systems. And since the workflows communicate via files, the file system type is obviously an issue. And you might have a mismatch between the tasks and the architectures, such as single core tasks on HPC systems. So throughout the years, we addressed a number of these issues. In terms of resilience, so what actually has helped us was this notion of virtual data and allowing for generating data on demand or reusing the data that's already available. So for example, if you look in this, the middle workflow, it's assumed, so you start off with an abstract workflow. Let's assume that already file f.d existed somewhere. So somebody did part of the computation and made the file f.d available. That means if you run this plan this workflow, you actually just need to execute the rightmost branch of a workflow, and thus you save time. And this is also helps you in case of failure. So for example, if you're executing this workflow and the workflow progressed to task D, but somehow f.a got corrupted before it was consumed by task C, you can resubmit the entire workflow, and you can replan from the beginning, running task A to generate f.a, but you don't need to run the other tasks in the workflow. So this allows you to basically have resilience in the workflow execution. It provides you with data reuse. And also, so you can think of it, you have workflow level checkpointing that helps you with efficient executions in case of failures. Another issue is basically managing the data flow within the workflow. So if you're running on an HPC system, you're starting from where the workflow engine is at the user side. We call that the submit host. It sends a job to a particular compute site that has a shared file system. In this case, we stage the data to this file system, and then the tasks can execute. And when the tasks are generating the data, it's staged out to the local file system, and then we can stage it out at the end of the execution. So situations can be a little bit more complex. For example, if we run in a distributed environment or a cloud, we have this notion, we don't have a shared file system, so we have a notion of a staging site that holds the input data. And then when the tasks are being scheduled onto the resources, Pegasus pulls the data automatically from the staging site for the execution of the tasks and puts the results back when the tasks have finished. Obviously, the advantages are that you can use cloud resources with scalable stores, and you get good bandwidth to the data. But you also have duplicate file transfers, and you have also latencies when you're transferring a large number of files. If you're running on cloud resources and you're pulling data from the cloud to a cluster, that also can incur costs. However, that's still a feasible solution, and that allows you to build up to something more complex, where you have basically, you can run on various compute sites, with some of them with shared file systems, some of them with different types of access to remote storage resources. So one thing that you need to do, however, when you mix and match these various resources, you need to have a way to move data between them. And so we developed the Pegasus transfer system, which allows you to talk various protocols. So it talks HTTP, SCP, and so forth. It connects to Amazon S3, Google Storage, and it basically allows you to not only talk these various protocols, but also it allows you to talk between protocols that are not compatible. So it does two-state transfers. So if you want to do grid FTP to an S3, you can do a grid FTP to a local file and then local file to S3, for example. It also does automatic retries in case of failures. It can do parallel transfers, and it checkpoints and restarts in case of failures, and can go to the next data replica if that's possible. And this also is related to some of the recent work we've done supporting containers. So a lot of people are using darker or singularity in the work. So now in our workflows, we can bring in the images from a hub, and then we stage them on demand to the resources where the computations are being executed. Obviously, this helps with sometimes once the container is on the resource, we basically checkpoint it there, and we can reuse it for our other computations. And it also allows you to not go to the hub every time you need to stage a container. In terms of optimizations that we've done over the years, we optimized the workflows in terms of storage. So for example, at the beginning of our collaboration, LIGO wanted to run on the Open Science Grid, and their workflows were quite data intensive, and at the time the Open Science Grid didn't have enough storage to run them. So we looked at various algorithms that can be used to clean up the data as the workflow is executing. So we added these special data cleanup nodes that basically delete the data from the execution site once the data is no longer needed by the subsequent computations. And as a result, when we're evaluating these optimization techniques, we looked at the Montage astronomy application, which is out of Caltech. And this shows you the execution of a workflow over time. It's time in seconds and versus the space in megabytes used by the workflow. The original execution is shown in green, and basically as the workflow is executing, it's taking up more and more storage on the compute resource, going up to, in this case, to 1.25 gigabytes, versus if you go and you clean up the data as you go along, you are able to reduce the footprint to 700 megabytes. So we felt that this was a good success for that application. We looked at it for LIGO. Unfortunately, when we first looked at with the simple transformations for LIGO, because the structure of a workflow is, as you see on the left, it actually needs to bring in all the input data and keeps it for a while before it actually you can do any cleanup. So at first we didn't get any improvements in the storage space for LIGO. Then we developed new algorithms that would transform the workflow in a way that would allow us for a 26% improvement in storage. However, when we went to the LIGO scientists and showed them what we did to the work, they were not very happy. So we abandoned that. We still have the data cleanup algorithms in our codes. However, we don't have this kind of work for restructuring. We just do the restructuring. We just add the nodes in a simple fashion. Another application we've been working with over the years is from the Southern California Earthquake Center, and it's called the CyberShake application. And the scientists basically generate maps of shake maps of Southern California, where you can graphically show the predictions of the shaking that you can expect in a particular area of Southern California over the next 50 years. And this is information that's very valuable, for example, to civil engineers, because when they build buildings in Southern California, they can figure out what type of tolerance they need to put into the buildings to withstand the earthquakes. In the case of SCEC, what they have is they have first MPI workload, or part of the workflow runs MPI calculations to do mesh generation and others. And then after you generate the results, you have to do a lot of post-processing. So you actually have, for a map like this, you have about 300 of these workflows that need to run. But each of these workflows has maybe 3 MPI calculations followed by over 800,000 single-core tasks. And because there's a lot of data transfer between the MPI computation and the sequential tasks, you really want to collocate them on one system. So oftentimes SCIAC runs on HPC clusters. They run both parts of a workflow. However, you have a problem of now fitting in 800,000 tasks of a particular workflow on an HPC system. Obviously, you cannot queue them to that degree, and you are not making use of system efficiently if you queue them one by one. So we developed various techniques to alleviate. So one of them is task clustering. So we cluster the tasks into larger holes, and then we schedule them as a unit onto the remote resource. And then the tasks are executed sequentially on an HPC system. So at this point, you are basically reducing the number of tasks that flow through the scheduler, and you also increasing the computational granularity of these tasks. Another solution that you can combine with that is to do guidance or submitting pilot jobs to HPC resource. So you submit a pilot job that runs over time, and you pump the tasks through that pilot. So you can use, for example, the guidance in HC Condor to do that. And as a result, you're bypassing the scheduler for the smaller tasks. So you reduce the load on the scheduler. And then finally, you can also partition the workflow and then manage pieces of the workflow as you see next. You can basically put a piece of use the software to develop Pegasus MPI cluster that takes a whole sub-workflow. It is shipped along with that sub-workflow to the HPC system, and it runs in master worker paradigm where it basically uses MPI to send out jobs to the worker nodes on the HPC cluster. So from the point of view of a cluster, this looks like a typical MPI application. However, you're using the machine to do large-scale processing of single-core workloads. Another direction that we are currently exploring is looking at data integrity within workflow applications. And this is because in distributed systems and when you have large amounts of data that flow through the workflow, we postulated that you might have errors in the data transmission. So we wanted to provide additional assurances that data was not modified, and obviously this is very relevant and important to scientific reproducibility. So we started adding nodes to the workflow that run checksums on the data as it's coming in and being used by the application. So before f.a is used by hello, it's actually its signature is checked. And then as you create new data, you also create checksums for the new data product so you can use them again. And so we tried to figure out whether this would actually catch any errors with this approach. We asked our users to install new versions of Pegasus, users that were running on the Open Science Grid. And we took 4 of these applications. 2 of the users sent us information about the workloads. One of them is a system biology application. It's called OSG-Kink. And it performs gene expression analysis. Another one is a population modeling workflow, which is used to trace population migration through Europe, for example, over time, and they're looking at DNA analysis to be able to track population migration. There's also the dark energy survey weak lensing workflow, which measures the shape of galaxies in a given region. And Veritas, which compares telescope images with simulated ones to be able to figure out whether you're looking at a cosmic ray shower or a gamma ray shower. So first of all, we wanted to see the cost of integrity checking. So for these 3 of these workflows, we had information about the number of jobs. So in this case, the population modeling had about 5,000 of jobs. So to run, it took 167 days to run them. The time to compare the checksums was almost 3 hours. but it's really just a very small fraction of our execution time. And then, similarly to the weak lensing and the bioinformatics workflows, you also see that the overheads were quite minimal. We also, during the execution, we detected some errors. So in the OSG King case, we saw 60 errors during this 17-day period. And it turned out that the errors were due to data caching. So the workflows pulling out data that was stale. And there are also others that, in the Veritas case, the astronomy, it turned out that the file transfer tools that we're using also had some errors in them. So normally these errors would not be detected by the system. However, with this new approach, we're able to see them. Another thing that's been useful in managing large-scale workflows or workflows that basically form workflow ensembles is to use a workflow manager, workflow ensemble manager, where we can submit various workflows and various ensembles to the system. And each of these workflows can be then planned and executed in parallel. The problem, obviously, here is resource usage, so you can use up a lot of resources quite fast. So you might want to prioritize the workflows. You might also set limits on how many workflows you're running at a particular time. But in general, you can start up an ensemble, you can pause it, you can resume it, remove various workflows, you can replan things or re-execute. And we also provide debugging mechanisms to help you figure out if something goes wrong. Finally, we're also adding new features that would start up workflows on events as they occur. Finally, talking about future directions. So one of the things that we really want to improve is the ease of use of the tools, and also focusing on the data management. And so we want to be able to have better solutions to perform analysis on data coming from sensors and instruments. We also want to add data management as first level primitives to workflow composition, so you can operate on data based on these directives. We also want to be able to do more analysis on the fly, and we're looking at more of a coupling or in situ type of workflows that were mentioned in the talk earlier. How do you combine a couple of these simulations and data mining, for example, or visualization? And we're looking at reusing some of the tools that were described, such as data spaces, for that purpose. And obviously, reproducibility, transparency, and reuse are very important to the scientific method. And so we're trying to figure out how we can improve that and how we can publish the workflows in a reproducible way. Another direction that we're going into is, I showed that there are various errors that happen in particular, we look just at data transfers, but there are a number of different failures that happen in the system. So we want to be able to detect them as soon as possible, and we want to have automated ways of figuring out whether a particular workflow is going to succeed or is doomed to failure. So we adding information to Pegasus normally just goes through this Pegasus wrapper kickstart to a database, and then we can do some workflow level analysis and visualization. However, we're also adding new events that can that can detect errors earlier in the process, and we store it in a time series database and also in an Elasticsearch, so we can run various analysis. Our collaborators from Renzi, in particular Anubhav Mandal, have been doing a lot of looking at anomaly detection in the workflow execution, looking at the workflow level. So he designed various decided on a set of features that he wants to look at within the workflow execution, and used the k-means clustering to see if he can detect these various clusters of jobs. So the various features that he looked at are the job instances that succeeded as a proportion of the jobs that were done. Also the failed jobs, as well as the sum of the duration of the jobs that were successfully executed versus the ones that finished. And same thing for the failed ones. And then he ran experiments where he introduced failures into the workflow. And you could see that these were the clean runs of the workflow where no failures occurred. So they are clustered around this area on the bottom. Whereas the failed clusters definitely show a different signature and different placement in the space, so that you can tell as the jobs are starting to fail whether the workflows are kind of doomed for failure. In general, and I think Francois was mentioning in his talk the issue of resource management, and this is very important across the various infrastructures that the scientists are running on today. So as was mentioned earlier, HPC systems are becoming more complex, they are becoming more heterogeneous. They have very specialized data stores, so for example, bus buffers, NVRAM, and so forth. And they are increasingly faulty. So in some sense, they look more like, keep looking more like distributed systems with heterogeneity, failures, and complexity. The distributed systems themselves have become more complex. You have a number of different software-defined capabilities that you can put into play. So you have software-defined networks and exchanges, for example, that you can utilize for executing your workload. You have also very specialized data storage, such as data transfer nodes, that also are part of the mix. So you have a lot more of scheduling decisions and resource management decisions that need to be done. In terms of clouds, obviously that's also a new platform for science. They've been used, as you know, in the business community quite a bit. But because they are very heterogeneous and very costly, or can be very costly, we need tools that help users manage their workloads on these resources. So issues of estimating which types of resources are best fit a particular workload, how can you do computing on a budget? These are all things that clouds and other systems need to be managed on behalf of a user. In terms of faults in the environment, not only detection but also attribution of these faults is important so that you can automatically recover from the errors. Dealing with heterogeneous storage is also obviously a problem. And then when we're talking about automation and managing these workflow ensembles, they are very challenging to manage because, as I mentioned, resources, they can consume a huge number of resources quite quickly. So you need to be able to keep track of that. And obviously there's a lot of advances in the big data technologies and machine learning solutions that are really exploding right now. And so even keeping track of what's going on is challenging, but I think a lot of these technologies can be applicable. So in the last few minutes, I just wanted to talk a little bit about the new effort that so my collaborators and I have started. And this is in recognition that just like in LIGO, cyber infrastructure is a critical component of science today, especially when it comes to these large facilities, as NSF calls them. So these are large-scale instruments that, in these cases, they are mostly in the US, but also they have international collaborations. So you have LIGO, for example, you have the National Radio Astronomy Observatory, which has various radio telescopes. You have NEON, which is ecological large facility that looks at different aquatic and terrestrial systems. And OI, which Ocean Observatory Initiative, which tries to understand the coastal ecosystems. And so all these large facilities have in common a large amount of cyber infrastructure for data collection, data analysis, data distribution to the users. However, all of them are building their infrastructure independently of each other. And so a challenge is how do you how do you share knowledge between these large facilities, and so that they can take advantage of work that others have done, and that others can take advantage of their work. So in September of 2017, we organized a workshop that looked at the cyber infrastructure of large facilities. And there are some key recommendations from that workshop. One was to try to establish a center of excellence that could collect the various effective best practices of the large facilities, so that this knowledge can be shared with other projects as they are starting up and operating. They also recommended that such a center would enable the various communities, cyber infrastructure communities, to interact and collaborate. Also, there was a recommendation to create a portal which is curated and a knowledge base about various cyber infrastructure components and services that are available out there, and how to best use them in various circumstances. And also the issue of workforce development, training, and retention was very important to the workshop attendees as well, as it's becoming more and more difficult to have a team of experts in the cyber infrastructure area. So in October of 2018, NSF has funded our project. This is a collaboration between USC, University of Notre Dame, University of Utah, and Indiana University in Renzi. And the goal of this project, it's a 2-year effort, and the goal of this project is to develop a model and a plan for a cyber infrastructure center of excellence. So we're talking to these various facilities and other large cyber infrastructure projects, trying to figure out what would be useful, what are the activities that would be useful for such a center to be established. So we want to be a platform for knowledge sharing as well as community building. We want to be a key partner in establishing new large facilities. So as new projects come up, we wanted to be there to share the knowledge from the previous efforts. And we want to make sure that the tools the community is developing are also used efficiently and effectively in these various projects. We also want to provide a forum for discussion about issues of workforce development. And currently we've engaged with selected few projects for this pilot. We engaged with ecological network NEON. They are currently undergoing a cyber infrastructure enhancement, so we feel that we are good partners where we can leverage each other's knowledge moving forward. And we're also engaging with other large facilities, and we'll do more engagement in the second year. I'm also very interested in finding out how large projects such as this develop in Europe, and how the cyber infrastructure within these projects is managed, and maybe we can also cross the knowledge, share the knowledge across the pond. So in conclusion, I talked about our experiences with Pegasus workflow management software, and hopefully shared with you the notion that developing production quality software that's used by scientists for a long amount of time takes time. It also needs sustained funding, so we've been able to receive funding from the National Science Foundation, from the Department of Energy, the National Institutes of Health. We've done a number of different algorithms of development, and I just shared some of them with you today. Throughout, it's been a close collaboration between us computer scientists and within different groups of computer scientists and domain scientists. And I think this has been critical to make our software relevant. It's also important to listen to the user's needs, but then to try to abstract them to something that's broadly applicable, so that you don't develop things for a particular user, but really across domains. And it's important to have a commitment to the vision and to the collaboration that you're building over time. And last but not least, it's you really need a great team, and a lot of people that have been on my team have been with me for a very long time. For example, Karen has been started in 2001, and others have been more than 10 years with me. And also we have a number of students, and we welcome visitors. So if people want to come and spend some time with us, Rosa, for example, from University of Edinburgh, has spent several months with us working closely on various projects. So we welcome visitors and graduate students. Thank you.
Question for Eva?
So thank you, Eva, for a great talk. So I'm curious about workflow splitting, which you mentioned maybe in the slide 50 or something. So I'm curious that to optimize the splitting or a disjoint point, so we perhaps the system need to know the amount of the data transfer on each task, between each task. So how do you estimate, or how do you get the information about that?
So we use historical information. Basically, we have workflow profiles that we can develop from the historical data. And oftentimes, scientists run the workflow a number of different times. So it's like a one-shot thing. So it's really whole workflow campaigns that are being run. So usually you can collect the data, at least initially, to some extent, and then project out.
I see. Sorry, maybe you introduce machine learning or something.
Yeah, that too. Yeah.
Thank you. More questions? I have one. When you talk about visualization, data mining inside the HPC supercomputer, you want to do that online. Do you have an idea, or you want to do that? Or to implement that? What is required in the infrastructure to get that working?
Yeah, so I think it's it's a challenging issue, because one thing that we would like to do more resource management within a HPC system. And for that, you need some collaboration from a scheduler. And so far, the schedulers on these machines have not really developed capabilities, have not changed that much over time. However, there are new schedulers coming out of Lawrence Livermore National Lab, so the Flux scheduler, which seems to have more capabilities that would allow some discussion between the workflow management system and the scheduler. And I think maybe as we need more of these capabilities, the commercial schedulers will also kind of start developing them.
Okay, thank you. The last question? No, so thank you, Eva. We move to our next speaker.